Think about light. What comes to mind? Maybe it's the soft glow of the morning sun filtering through your window. Perhaps it's the gentle light from your desk lamp that lets you read a book late at night. Light seems intangible, weightless, and fundamentally harmless. You can pass your hand through a sunbeam and feel nothing but a little warmth. It doesn't push you. It doesn't stop you. For all its importance in letting us see the world, light seems, well, a bit weak. It's the opposite of something solid and strong, like a thick sheet of steel. But what if I told you that this same gentle, seemingly powerless thing could be turned into a tool of immense power? What if that same fundamental stuff, light, could be transformed into a blade sharp enough to slice through solid steel as if it were a block of cheese? This isn't science fiction. It's a reality that happens every day in factories all over the world. The very essence of sunlight can be disciplined, focused, and amplified to become one of the most powerful cutting tools ever invented. This is the world of lasers, where we take something as common as light and turn it into an invisible sword. The idea seems counterintuitive, almost magical. How can something without mass, something that travels in waves, exert enough force to sever a material known for its strength and resilience? The answer lies not in changing what light is, but in how we organize it. Imagine a crowd of people walking randomly in a public square. To understand how a laser can cut steel, we first have to understand why the light from a flashlight cannot. Both are forms of light, but they are profoundly different. The light from a lamp is like a chaotic jumble of waves. The light from a candle is like a chaotic jumble of waves. The light from the sun is like a chaotic jumble of waves. Think of it as dropping a handful of pebbles into a pond. You get ripples spreading out everywhere, of different sizes, moving in all directions and interfering with one another. This light is what we call incoherent. Its waves are a messy, disorganized mix of many different wavelengths, or colors, all out of sync and traveling in a scattered fashion. Laser light is the exact opposite. It is the ultimate in organized light. Instead of a jumble of waves, it consists of light waves that are all perfectly aligned. First, laser light is monochromatic, made up of a single color or a narrow range. Second, it is collimated. The light waves travel in a tight, parallel beam that doesn't spread out much over long distances. This is why a laser pointer can create a tiny dot on a wall far away, while a flashlight beam spreads out and becomes faint. The most important property, however, is that laser light is coherent. This is the real secret sauce. Coherence means all the light waves are in perfect step with each other, like soldiers marching in a parade. The peaks of all the waves line up, and the troughs of all the waves line up. When waves are in sync like this, their energy adds up constructively. Instead of cancelling each other out, they reinforce one another, creating a single unified wavefront of incredible intensity. It's the difference between a disorganized mob and a disciplined army. So, while the light from a bulb scatters its energy in all directions, a laser concentrates all its power into a single, focused point. It's this combination of being monochromatic, collimated, and coherent that gives laser light its extraordinary properties. It's not a different kind of light. It's just light that has been forced to get its act together. So, how do you create this perfectly organized light? You can't just filter sunlight through a special screen. You have to build it from the ground up, atom by atom. The process happens inside a device we call a laser, which stands for light amplification by stimulated emission of radiation. The basic recipe is surprisingly straightforward. You only need 3 key ingredients: a gain medium, an energy source, an optical cavity, a pair of mirrors. It's like a special oven for light. The first ingredient is the gain medium, a collection of atoms, solid crystal, like a ruby, a gas, like a mix of helium and neon, or a liquid dye. These atoms can be excited. Atoms have different energy levels, rungs on a ladder. Electrons usually sit on the lowest rung, the ground state. The energy source pumps atoms up to a higher rung, often a flash of intense light or a strong electrical current. Aim: more atoms excited than in ground state. Population inversion. Now the magic. Stimulated emission. An excited atom will fall back down and emit a photon. That photon can pass an excited neighbor and trigger another photon. The new photon is an exact clone. Same color, same direction, perfectly in sync. Phase-aligned waves. One photon becomes two become four, and you get a chain reaction. The optical cavity harnesses the chain reaction. The gain medium sits between two mirrors. One mirror is fully reflective. The other is partially reflective. Lets a little light out. Photons bounce between the mirrors through the medium repeatedly. Each pass stimulates more identical photons. Amplification. The beam grows until it escapes the partially reflective mirror as a concentrated, coherent, and powerful laser beam. This transformation from a gentle glow to a high-powered industrial tool is one of the most fascinating stories in modern physics. We've made a laser beam. It's organized, it's intense, it's ready to do some work. But how does this beam of pure light actually cut through steel? The process combines extreme heat and physical removal of material. It's not a blade in the traditional sense. It's more like a hyper-focused death ray. It melts, it vaporizes, it blows material away. It all starts by converting light into heat on a microscopic, incredibly rapid scale. When the concentrated laser hits steel, that immense energy is absorbed. This isn't the gentle warmth of the sun. It's energy packed into a spot smaller than a human hair. The temperature at that tiny point skyrockets almost instantly. It reaches steel's melting point, around 1500 degrees Celsius or 2750 Fahrenheit, in a fraction of a second. Melting alone doesn't make a clean cut. You must remove the molten material. Industrial cutters get help from a high-pressure gas jet, oxygen or nitrogen. Oxygen reacts with hot steel in an exothermic reaction, adding heat. The gas also acts like a focused hurricane, blowing molten steel out of the cut, the kerf. As the laser head moves along its path, this repeats. Heat, melt, and blow away. The beam penetrates deeper, creating a narrow, clean channel. The result is an incredibly precise cut with a tiny heat-affected zone. With extremely powerful lasers, the steel can vaporize. It goes straight from solid to gas. Sublimation. That's how lasers can cut with almost no mess or leftover molten material. One of the most remarkable things about laser cutting isn't just the raw power, but the incredible finesse it offers. A laser beam doesn't physically touch the steel it cuts. No mechanical stress, no warping. The laser cutter is guided by CNC from CAD designs, translating blueprints into precise motion. Just as there are many types of saws for cutting different materials, there are many different types of lasers, each suited for specific tasks. The choice of laser depends on the material being cut, the required power, and the desired precision. The gain medium is what defines the type of laser and the color, or wavelength, of light it produces. Different materials absorb different wavelengths of light more efficiently, so choosing the right laser is crucial for an effective cut. One of the most common workhorses is the CO2 laser, a mixture of carbon dioxide, nitrogen, and helium gas. CO2 lasers produce far-infrared light, invisible to the human eye. This wavelength is excellent for cutting, boring, and engraving a wide range of materials, including steel, plastics, wood, and acrylics. They are powerful, reliable, relatively efficient, the sledgehammers of the laser world. A more recent and popular type is the fiber laser, where an optical fiber doped with ytterbium generates and amplifies light. This architecture is compact, robust, and energy efficient. Fiber lasers produce a much smaller focal spot, leading to higher power density. Their wavelength is better absorbed by metals, enabling faster, more precise cutting. Even on reflective materials like brass and copper, especially thin steel sheets. End-YAG lasers use a YAG crystal doped with neodymium. They can deliver extremely high power in short pulses, Ideal for welding, drilling, and cutting. Excimer lasers produce ultraviolet light that can break molecular bonds directly, enabling photoablation for microfabrication and delicate eye surgery. While the image of a laser slicing steel is dramatic, it's just one application. Lasers have quietly integrated into nearly every aspect of modern life, often in ways we don't even notice. Because a laser can be focused to a tiny spot, it can cut or vaporize tissue with pinpoint accuracy, causing minimal damage, less bleeding, and faster recovery. From LASIK to kidney stones, tumor removal, and skin therapy. Every time you stream, call, or browse, pulses of laser light race through fiber optic cables across continents and under oceans. At home, blue-violet lasers read Blu-ray discs, red lasers scan barcodes, and laser printers write images with light. We even measure the distance to the moon with centimeter accuracy, and paint the sky with dazzling shows. From the mundane to the monumental, lasers have become a fundamental, transformative tool for humanity. For all their amazing capabilities, lasers, especially high-power ones, present significant challenges. Wielding a tool that can vaporize steel requires incredible control, sophisticated engineering, and respect for danger. The same properties that make a laser powerful also make it a hazard that must be managed. Lasers are not perfectly efficient. Much of the input energy becomes heat. For kilowatt-class lasers, waste heat is enormous, enough to damage delicate components. Complex cooling systems with chilled water keep lasers stable. Managing this thermal load is a major engineering hurdle as we push to higher powers. Safety is paramount. A cutting beam can cause severe, instantaneous injury. A direct or reflected beam can cause permanent eye damage in a fraction of a second. Operators wear wavelength-specific goggles, and interlocks shut lasers down if enclosures open. The skin can also be severely burned. At high power, thermal lensing can distort the gain medium and degrade beam quality. Optical components must withstand intense beams without damage. Pushing boundaries means inventing new materials and techniques to handle extreme conditions. Taming the laser beast is a continuous quest to balance immense power with perfect control. And yet, with each challenge solved, lasers open new frontiers, from manufacturing perfection to medicine and beyond. The journey of the laser, from a theoretical concept to a world-changing tool, is far from over. If the past 60 years have shown us anything, it's that the potential applications are limited only by our imagination. As we refine laser technology, we stand at the brink of breakthroughs that will shape our future. The light that now cuts steel may one day build structures on other planets and power exploration. One exciting frontier is energy. Scientists pursue nuclear fusion, the process that powers the sun. At the National Ignition Facility, 192 of the world's most powerful lasers focus on a tiny hydrogen pellet to achieve the heat and pressure for fusion. If successful, laser-driven fusion could provide a nearly limitless, sustainable power source. Laser sails could push ultralight spacecraft to a fraction of light speed, enabling missions to nearby stars within a lifetime. Lasers could sweep space debris from orbit, making space travel safer. Imagine 3D printers fusing metal powder into custom machine parts on demand. Think ultra-high-speed networks using lasers through air, a wireless fiber internet. In medicine, ever more precise lasers will target individual diseased cells without harming healthy ones. The light that once seemed so gentle is now one of our most powerful and promising tools. The future, it seems, will be forged by light, healed by light, connected by light. What started as a curious discovery in physics is now cutting steel, repairing hearts, and shaping tomorrow. The next time you see a laser pointer, remember, you're holding one of humanity's most brilliant uses of light.